Hello children, welcome back to the channel. We are in the middle of our discussion of rotational motion of rigid bodies, and we are dealing with moment of inertia and other physical quantities and their relationships. Today we have come to the topic of torque and moment of inertia. Now we will consider that there is a rigid body of some shape rotating about a given axis under the influence of a force, or which in other words would mean that there will be a torque on it, which means that there is a constant acceleration, or there is an acceleration, angular acceleration of the body. We will say that angular acceleration is alpha. Okay, so the torque that is acting on the body, tau, will be distributed among each of the bodies, because all the bodies will experience certain amount of torque, and as a result it will have angular acceleration. So let us say particle 1 has a torque tau 1, second one has torque tau 2, and so on and so forth, and the nth and the last particle experiences a torque of tau n. So net torque will be sum of these all torques, right? Now what we need to note here is that we are saying that the body is moving in a circular path. So when it's moving in a circular path, what will happen is that the direction of the force will be perpendicular to the path, right? Which means the torque will be, what will happen here is that say the first particle will experience certain amount of force, and as a result of the force it will have an acceleration. Let's call this A1. Second one will also have an acceleration, A2. Third one also will have A3. All of their magnitudes are different. However, since the torque acting on it is different, and as a result each of their linear acceleration will be different. However, because their positions are different, in the sense that their distances from the given axis of rotation are different, so their angular acceleration will remain the same, and that is going to be alpha. Okay, so by definition of torque, we know that if the force and the radius vector are perpendicular to each other, what we will know is that torque's magnitude can be given by F into R. So tau 1 will be equal to F1 into R1. Similarly, tau 2 will be F2 into R2, and so on till Fn Rn. What we have considered that the force and the radius vector are perpendicular to each other. Okay. However, by definition, from Newton's law, second law, since this force F1 develops an acceleration, or gives an acceleration of A1 to the particle m1, so F1 will has to be equal to m1 into A1 and then into R, plus F2, instead of F2 we will write mass 2 is accelerated with a linear acceleration of A2, so it will be m2A2 and then multiplied by R2, and so on till the nth particle, which will be mn an multiplied by Rn. Okay, now for a particle, if we consider individual particles, say m1 is moving with a linear acceleration of a1, so it will be equal to r1 into alpha. A particle moving in a circular path with radius r, then the linear acceleration and angular acceleration are related by this particular relation, a equal to r alpha. So a1 will be equal to r1 into alpha, then we have r1, m2, a2 will be equal to r2 into alpha. Alpha is constant, same for all the particles, r2, and so on till mn Rn into alpha, then Rn. If we simplify this, what we get is that m1 R1 squared plus m2 R2 squared plus mn Rn squared, whole thing multiplied by alpha. alpha, taking alpha common from this. Now what we know from definition of moment of inertia, we know that moment of inertia of a rigid body about a given axis is sum of m1 r1 square plus m2 r2 square, right? So this term is equal to the moment of inertia of the body about the given axis. Therefore we can say that torque is equal to I into alpha. Okay, so moment of inertia and torque are related by this particular expression. Now for a special case, if we have alpha equal to 1 for unit angular acceleration 1 radian per second square, that is, what do we have? Tau equal to I. That is to say that the moment of inertia of a rigid body about a given axis is numerically equal to the torque acting on it, or torque that produces a unit acceleration in the body. Moment of inertia about a given axis is equal to the torque, numerically equal to the torque, not exactly equal to, numerically equal to the torque that produces a unit acceleration in the body. Unit angular acceleration in the body, not unit acceleration. Okay, so this is what is the relationship between moment of inertia and torque. Okay, now let us take up the case of angular momentum and moment of inertia, if there is a relationship between these two also. So let us consider that a rigid body moving about a given axis with an angular velocity of omega, which means each of the particle will have a linear velocity like v1, second particle has a linear velocity of v2, say, third one has a linear velocity of v3, and so on and so forth. Okay, so the net angular momentum, see, the rigid body is moving about a given axis, and so the angular momentum of the system or the rigid body L will simply be the sum of angular momenta of the individual particles, right, about the given axis till nth particle, say. Or by definition we know it is equal to P1 into R1 plus P2 into R2 till Pn into Rn, where P1, P2, P3, etc. are the linear momenta of the given particles m1, m2, m3 respectively, and R1, R2, R3 are their distances, respective distances from the axis of rotation about which it is moving in a circular path. Okay, however, linear momentum by definition for first particle will be m1 v1, where v1 is the velocity of the first particle into r1. Similarly, m2 v2 into r2 for second particle, and so for nth particle mn vn into rn. However, we know for a particle moving in a circular motion, v is given by r omega. So for first particle it will be r1 omega, for second particle it will be r2 omega, and so on and so forth, because omega angular velocity is supposed to be or taken to be constant here. So we have m1 r1 omega into r1 plus m2 r2 omega into r2 till mn rn omega into rn till the nth particle. So again, if we take omega outside, what we get? m1 r1 squared plus m2 r2 squared till mn rn squared, whole thing multiplied by omega. Or in other words, we can say that L, that is angular momentum, net angular momentum of the rotating body about the given axis, is equal to moment of inertia of the body about the axis multiplied by omega. Okay, so this is another important expression and relationship between moment of inertia and angular momentum. Now if we consider like the previous case, if omega equal to 1, that is the angular velocity of rotation is 1 unit, that is 1 radian per second, then L becomes equal to I. So we can define moment of inertia this way also, as we did in case of relationship with torque, that moment of inertia of a given body rotating about a given axis is numerically equal to the angular momentum of the body when it is moving with unit angular velocity about the given axis. For unit angular velocity about a given axis, moment of inertia of the body will be numerically equal to the angular momentum of the body. Okay, this is expression L is equal to I omega, and also the expression of torque tau equal to I alpha. These two are very, very important and will be very, very useful in problem solving that you will come across in problems of when you try to solve problems in this chapter, that is rotational motion of rigid bodies. Let's tackle a couple of problems now, simple ones. The first one says that if the radius of Earth spontaneously reduced to half of its current value, if R is the current radius, the new radius becomes R by 2, then what will be the duration of day? Are we clear? Radius of Earth spontaneously reduced to half of its current value, what will be the duration of day? Okay, so first of all we need to notice, let's say current radius of Earth is say R, and current duration of day is 24 hours, that we know. It says that if R2 becomes R by 2 without any outside intervention, then what will be T2? That is the question. Okay, now what we need to notice here is that it says that the radius reduces spontaneously without any outside intervention, which means there is no external torque acting on the system. If there is no external torque, then we must have the angular momentum conserved, that is L1, angular momentum before or current before the radius was reduced must be equal to angular momentum after the radius has been reduced to the new value of R by 2. Okay, so after the Earth has shrunk, the new angular momentum and the angular momentum before the Earth has shrunk has to be same by conservation or of angular momentum. If it is so, then we know that will mean that the moment of inertia, the current moment of inertia of the Earth, or the prior to the shrinking of Earth, the moment of inertia multiplied by the angular velocity must be equal to I2 by into omega 2, because we have just found that L is equal to I omega. Okay, so this will give us what is I. Now Earth is we can consider Earth to be a solid sphere, uniform solid sphere, and it is rotating about its axis. So we will have to make use of the formula for moment of inertia of a uniform solid sphere about its axis, and which is 2 by 5 m, if m is the mass of the Earth, into r1 squared, which is r squared. Okay, this is the moment of inertia, and we also know that omega can be given by 2 pi by time period from circular motion. Okay, so this will be 2 pi by t1, this one. This must be equal to 2 by 5 m r by 2 whole squared, because radius is r2 is r by 2 multiplied by 2 pi by t2. Now we clearly see this cancels, 2 pi's will cancel, m's will cancel, r squares will cancel. So what do we have? 1 by t1 equal to this is half squared, right? 1 by 4 T2. This gives T1 equal to 4 T2, or T2, the new time period will be T1 by 4, which must be equal to 24 hours by 4, that is 6 hours. So, if the radius of the earth spontaneously shrunk to half of its current radius, the time period of day, that is duration of day, will be 6 hours. Okay. Our next problem, quite similar one, is that if the volume of the earth suddenly become 1 by 64 times, 1/64 of its current volume, then what will be the new duration of the day? So if I say volume of the earth is V1 currently, then if V2, the new volume will be V1 by 64. In that case, T1 we already know, 24 hours. What is going to be the duration of the day, or the time period of rotation of earth? So now here only problem is that we cannot use the formula directly as we did in the previous case. First we need to notice is that moment of inertia depends on the radius, right? We are not being given radius. So what we'll say, we'll assume that current radius of earth is r, which will give us that volume of earth will be 4 by 3 pi r cube, current one. So V2 will be 4 by 3 pi r cube by 64, which will be equal to 4 by 3 pi r by 4 whole cube, right? 4 cube is 64. Therefore, we can say that if R1 equal to R, then R2 will be equal to R divided by 4. So we have found a relationship between the radii before the shrinking has taken place and after the shrinking has taken place. Now we are in a position where we can make use of our formula. That is, we will make use of conservation of angular momentum. Since the volume shrunk spontaneously without any outside intervention, so angular momentum must be conserved, which will give us I1 omega 1 equal to I2 omega 2, just like the previous case. So since our earth can be considered to be a solid sphere, uniform solid sphere, it will be I1 will be, sorry, not 3, 2 by 5 m is the mass of the earth, r squared, okay, r1 squared, that is r squared, into omega 1, that is 2 pi by t1. This will be equal to 2 by 5 m r by 4 squared, right? So r by 4 squared is r squared by 16, since r2 equal to r by 4. So we have directly substituted the value, this thing multiplied by 2 pi by t, 2. So mr square cancel, 2 by 5, 2 pi by 5 cancels, pi's cancel. So we have t1 equal to 16 t2. That is to say, t2 must be equal to t1 by 16, which is equal to 24 by 16. So this is 4, this is 6. That is to say 3 by 2, or we can say this is 1.5 hour. So the new duration of day will become 1.5 hour.